Hello everyone, myself Soumya Vijay, Assistant Professor, Department of ECE, SJBIT. Subject is Digital Communication and the subject code is 18EC61. I am discussing about digital modulation techniques. In digital modulation techniques, in the previous session, we have discussed about the phase shift keying technique using coherent detection, particularly BPSK. In this session, we will be discussing about QPSK. QPSK stands for Quadrilateral Phase Shift Keying or Quadri-Phase Shift Keying. QPSK stands for Quadri-Phase Shift Keying or Quadrilateral Phase Shift Keying. Let us now first discuss about the signal representation of this QPSK. The QPSK is one of the bandwidth conserving scheme. Here the phase of the carrier takes on one of four equally spaced values like pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. In quadriphase shift keying, we are representing four symbols. Each symbol will be having two binary bits. Each symbol is represented as 00, 01, 10 and 11. For each symbol, the phase of the carrier is been represented and they are represented as one of four equally spaced values such as pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. And the transmitted signal in quadriphase shift keying S of t is defined as S of t is equal to square root of 2e by t cos of 2 pi fct plus 2I minus 1 into pi by 4, and t ranges from 0 to capital T. In the remaining range, the value of S of t is 0. I repeat, the transmitted signal S of t is defined as S of t is equal to square root of 2e by t cos of 2 pi fct plus 2I minus 1 into pi by 4 for t greater than or equal to 0, less than or equal to t, and 0 for the remaining values of small t. In this expression, I value will be equal to 1, 2, 3 and 4. And E is transmitted signal energy per symbol. Capital T will be symbol duration. As I mentioned, in QPSK, each possible value of the phase corresponds to unique D bit. A D bit is nothing but the pair of the bits. 2 bits will be used to represent each possible value of the phase. For example, we may choose the set of phase values to represent the gray code and natural code. Now, moving on to the signal space diagram of the QPSK. If we expand the equation 1 using the formula, that is the trigonometric relationship, that is cos of a plus b equal to cos a cos b minus sin b sin b, we get S of t equal to square root of 2e by t cos of 2I minus 1 into pi by 4 into cos of 2 pi fct minus square root of 2e by t sin of 2I minus 1 into pi by 4 into sin of 2 pi fct. This we can take it as equation number 2. In this equation, the first term we call it as in phase component and the second term we call it as quadrature phase component. I value is again 1, 2, 3 and 4. This equation, which is labeled as equation number 2, is got by the equation 1 using cos of a plus b is equal to cos a cos b minus sin a sin b. Using this trigonometric relationship, we have expanded the equation 1, and accordingly we have got the equation 1 as s of t is equal to square root of 2e by t cos of 2i minus 1 into pi by 4 cos of 2 pi fct minus square root of 2e by t sin of 2i minus 1 into pi by 4 sin of 2 pi fct. In this expression, which is labeled as expression number 2, the first term is called as in-phase component and the second term is called as quadrature phase component. I value will be 1, 2, 3 and 4. Now based on this representation, that is equation 2, we can make two observations. The first observation is there are two orthogonal basis functions. As you can notice here, there are two orthogonal basis functions. One is in terms of cos, another in terms of sin, and they are defined by a pair of quadrature carriers. There are two orthogonal basis functions which are defined by a pair of quadrature carriers. Those basis functions can be represented as pi 1 of t and pi 2 of t. Now the equation for pi 1 of t will be equal to square root of 2 by t square root of 2 by t cos of 2 pi fct in the range t greater than or equal to 0 less than or equal to t. Similarly, pi 2 of t is equal to square root of 2 by t sin of 2 pi fct. Pi 2 of t is equal to square root of 2 by t square root of 2 by t sin of 2 pi fct for t greater than or equal to 0 less than or equal to t. Now in this expression of s of t, the coordinates of the message points are given by, we have segregated the basis functions from the expression 2. Now the remaining term will be pertaining to the message points. So the coordinates of the message points are given by si of t is equal to square of e square root of e square root of e cos of 2i minus 1 into pi by 4 minus square root of e sin of 2i minus 1 into pi by 4. Previously what we have done, we have taken the basis functions, we have segregated the basis functions from equation number 2. The first basis function is cos of 2 pi fct root of 2 by t into cos of 2 pi fct. The second basis function is square root of 2 by t sin of 2 pi fct. Now the remaining terms will be the coordinates of the message points, and they are given by si of t is equal to square root of e cos of 2i minus 1 into pi by 4 minus square root of e sin of 2i minus 1 into pi by 4. Here I value will be ranging from 1 to 4. 1, 2, 3 and 4. Now this is the table 1 which I mentioned previously, in which we have written the phase for the gray code as well as the phase value for the natural code. Here the elements of the signal vectors namely si1 and si2, their values are being summarized for both gray code as well as for the natural code. I value, as I mentioned previously, it is having 4 values 1, 2, 3 and 4, and si of t pertaining to I is equal to 1 will be s1 of t, pertaining to 2 will be s2 of t, pertaining to 3 will be s3 of t, pertaining to 4 will be s4 of t. Accordingly, the coordinate value si1 will be square root of e by 2, si2 will be minus square root of e by 2 for s1 of t. Similarly, for s2 of t, the coordinate value si1 will be minus square root of e by 2, si2 will be minus square root of e by 2, and s3 of t has got the first coordinate si1 as minus square root of e by 2, si2 as square root of e by 2. For s4 of t, the first coordinate value si1 is square root of e by 2, the second one is square root of e by 2. Accordingly, s1 of t can be represented by the d bit as 1 0 root of square root of e by 2 1 minus square root of e by 2 0, so 1 0. Similarly, minus square root of e by 2 0, minus square root of e by 2 0, so the d bit corresponding to s2 of t, the d bit corresponding to s2 of t will be 0 0. Similarly, s3 of t, minus root of e by 2 is 0, root of e by 2 is 1, minus square root of e by 2 is 0, root of e by 2 is 1, so the d bit corresponding to s3 of t will be 0 1. Now coming to s4 of t, s4 of t, square root of e by 2, square root of e by 2, so it is 1 1 1 1. The d bit corresponding to s4 of t is 1 1. Now let us write the phase both in Gray code as well as in the natural code. Once I go for the natural code, whatever representation I told you at the beginning of this QPSK introduction, that is, it has got 4 phase values: pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. The same thing in order will be applicable to this d bit of s1, s2, s3 and s4. That is, for d bit 1 0, it is pi by 4. For d bit 0 0, it is 3 pi by 4. For d bit 0 1, it is 5 pi by 4. For d bit 1 1, it is 7 pi by 4. Now coming to the phase of the Gray code, it is actually the reverse of the natural code. Whatever phase values we have written in the increasing order is pi by 4, 3 pi by 4. The same phases starting from s1 of t to s4 of t will be written in a reverse order. Will be written in a reverse order. It means for s1 of t it will be 7 pi by 4. For s2 of t it will be 5 pi by 4. For s3 of t it will be 3 pi by 4. For s4 of t it is pi by 4. Like this, the phase for the natural code and the phase for the Gray code can be written and summarized by means of this table 1. Now let us discuss about the signal space representation of the QPSK. The QPSK has got 4 message points and it is having a 2-dimensional constellation diagram. The QPSK has got 4 message points. Capital M is equal to 4 and it is having 2-dimensional constellation, that is capital N is equal to 2. The signal space diagram can be written in this way. We have got 2 phase, that is basis points pi 1 as well as pi 2. The pi 1 is on the horizontal axis and the pi 2 is on the vertical axis. Pi 2 is on the vertical axis. Now this is our decision boundary. And since there are 4 message points, we have 4 regions for this decision boundary. We are taking this as region Z1, this is region Z2, region Z3 and region Z4. Now the first message point is S1 and its d bit is 1 0 and its t bit is 1 0. This is the first message point M1, which we have taken in the table as S1 and its d bit representation is 1 0. And what are the coordinate values for this? It is square root of e by 2 and minus square root of e by 2. Square root of e by 2 for 1 minus square root of e by 2 for 0. Next, moving on to the region Z2, in which the second message point M2 is been considered. It has d bit representation 0 0. This is the one which we have taken as S2 in the table, and since there are 0 0, the d bit is represented as 0 0. The coordinate values will be minus square root of e by 2 and minus square root of e by 2. Minus square root of e by 2 and minus square root of e by 2. This is the values pertaining to 0 0. Similarly, region Z3, we have message point M3. The d bit corresponding to M3 will be 0 1, that is minus square root of e by 2 and plus square root of e by 2. Similarly, the message point M4 corresponding to d bit 1 1, this is the one which we have taken as S4. Since 1 1 is there, it has coordinate value square root of e by 2 and square root of e by plus square root of e by 2. And these coordinate values, whatever we have considered, square root of e by 2, square root of e by 2, square root of e by 2 minus square root of e by 2, these 4 points, they are being represented in the form of a, this is in the form of a square. Whereas if we go for other cases of modulation techniques, usually whenever we join the coordinates, whenever we join the points pertaining to the regions, we get a circle, but in this case we will be getting a square. Now moving on to the next part of this QPSK, that is waveform representation. Let us take an input binary sequence which is represented as 0 1 1 0 1 0 0 0. This is shown in actually this figure A. This is the figure A. In this figure A, the input binary sequence is being taken. As we know, in QPSK we are considering the symbol in the form of a D bit, means 2 binary bits representing one symbol. So this value of the input binary sequence is been considered in the form of a D bit. 0 1 will be the first D bit, next 1 0 will be the second D bit, next again 0 1 will be the third D bit, and 0 0 will be the fourth D bit. In this 0 1 will be first, next 1 0 will be second, next again 0 1 1 0, next again 1 0 will be third, again 0 0 will be fourth. Like this we are supposed to consider the input binary sequence in the form of the D bit. This sequence, as I told, it will be divided into 2 other sequences again. Those 2 other sequences I can call as one odd numbered bits of the sequence, another even numbered bits of the sequence. This sequence will be divided into 2 other sequences. One I call it as odd numbered bits of the input sequence, another I call it as even numbered bits of the input sequence. These 2 sequences are shown in the top lines of figure B and C. This is figure B and this figure C. The first one is representing odd numbered sequence. As we know, in the odd numbered sequence we are taking 0 1 1 0. It means in this 0 is odd number, 1 is odd number, again 1 is odd number, again 0 is odd number. Those sequences we are taking here, and the polarity of the coefficient x I 1 is considered. It is multiplied with the basis function pi 1 half t. After multiplication with the basis function, as we know, this is the representation that we get. This is 0, okay. 1, there is not phase shift, so it has to start at this point. Again 1, there is no phase shift, so it is starting at this point, okay. Next you are taking 0, there is a phase shift, so it has to start at this negative region with having a 180 degree phase shift. Next we are taking even numbered sequence, where the polarity of the coefficient is being taken as x I 2. We are multiplying that with the basis function by 2 of t. After multiplication we are getting this sequence here. As you can see here, this is even numbered sequence 1, this is 0, this is 0, this is 0. We are considering even numbered sequence here, okay. For even numbered sequence, since it is a even numbered sequence, after multiplying with the basis function you will get a pattern of waveform having no phase shift, so it is starting at this positive axis. Next after that we are having 0. So there is a 180 degree phase shift, 180 degree phase shift. Again 0 is there, so it is starting in the negative region. It is starting in the negative region. Again 0 is there, so it is starting in the negative region with no phase shift happening. Whenever it is moving from 1 to 0, there should be a phase shift. From 0 to 1, there should be a phase shift, but 0 to 0, no phase shift, 0 to 0, no phase shift. Similarly, 1 to 1, no phase shift. As you can notice here also there is no phase shift, but when the 0 is there, from 1, when it is been flipping to 0, it will be getting a 180 degree phase shift. Now, this is the final expression of x of t, which is the combination of this odd number sequence and the even number sequence. These two sequences together is resulting in this final waveform of x of t. As you can see, this is our final waveform of x of t, which is got by these two sequences, that is odd numbered sequence and the even numbered sequence. This is how the representation of x of t will be there in the case of QPSK. So, in this session we discussed about what is QPSK, how do I write the expression for the QPSK, what is the signal space representation of QPSK, and finally we understood how to write the waveform for the QPSK. Thank you.